Hello, my name is Sudhir Mallya, and I'm lead the corporate marketing group for Alphawave Semi, and it is my pleasure to deliver this webinar today. In this webinar, we will provide some key trends of in the data center connectivity, and also following that, we will cover why purpose-built silicon and system-on-a-chip solutions are of critical importance to the development of faster and more efficient data networks. And then I will summarize with some key takeaways from this presentation. Before I do that, I will give you a quick introduction of Alphawave and who we are, and an introduction of where we're based and so on. Alphawave was founded in 2017. We're a global company. We have offices in Toronto, Ottawa, Silicon Valley, London, also in Israel, and also across the globe over in India and Asia Pacific. Our mission is to be the world's leading provider of semiconductor connectivity solutions, and we provide DSP-based IP, very high-performance connectivity IP, custom silicon, and optical silicon products. We have over 700 employees, and our mission is to accelerate the connected world. We have some very exciting news. In the last month, we introduced a new brand, and we branded ourselves as Alphawave Semi. The rationale of the brand is now we are a vertically integrated company. Formerly, we used to be, as Alphawave IP, would be selling IP, but now that we have the ability to offer more to customers in terms of bringing IP and silicon to customers, we are now a truly vertically integrated company. One of the key things we will continue to do is maintain the technology leadership that we built on high-speed connectivity IP. And also, we have a very diverse, open, dynamic, technology-led culture. We have received several awards in terms of both on the technology front and also as a great place to work. So this is a quick overview of what we do. We offer connectivity silicon IP, which includes very high performance IP with SerDes, the controllers and subsystems, and targeted mostly for the networking, optical compute, storage markets, anything to do with AI and 5G infrastructure. Similarly, we offer custom silicon, which will be one of the main focus of the talk today. And then we also offer connectivity products, which include a high bandwidth targeted for optical and electrical networking. What I wanted to do was take a few minutes now to talk about the data connectivity market. And that will set the context for you in terms of the main topic, which is why the rise of custom silicon in these applications. This slide here shows the trend. I think it's one of the key things that is driving growth in this entire industry is the relentless growth in data. With the increase in sensors, devices, streaming services, the emergence of video everywhere, with the new recent things like ChatGPT, where people are using AI and the democratization of AI, the need for data continues to increase exponentially. And that is what is driving a lot of the demand for connectivity, right, in this space. At the same time, the connectivity requirements with the increasing amount of data, the connectivity is struggling to meet the bandwidth requirements. As you can see, the trends there, the data rates are doubling every 2 to 3 years. From a networking perspective, the switch data rates are increasing from 5 terabytes per second to 12 to today it's 25 terabits per second, moving quickly to 50 terabit per second switching. A lot of new technologies coming up. At the same time, the transceivers, that is the transceivers data rates are also correspondingly increasing. We're today at 100 gig PAM4 coherent and moving towards 200 gig. With all of this, there is still a huge, as I'll show you in the next few slides, one of the key barriers or the key things that is crunching the growth is the ability to meet the bandwidth. So I thought I'd spend a few minutes to give you some context of presenting the data center connectivity landscape. Uh, and this will give you an appreciation for why we need semiconductors, why semiconductors are so important in this, and also the role of custom silicon. So this slide shows you is a very good slide, I think, which shows you where data is getting consumed. And the interesting thing is, if you look at the data center, almost 70% of all the data center traffic is consumed inside the data center itself. And that is taking the data to the switches, doing the compute, and it's fueled by a lot of these applications, which is primarily AI driven. And then the other trend that is also happening is that at the edge, the rollout of 5G is a huge driver. Now you have people downloading videos, doing conference calls and video conference calls on their cell phones. That creates a huge amount of data requirement on the edge. And because of that, there are new baseband units and other things that have been installed in the edge, which are fueling more data in there too. So so there are two trends here. One is the compute happening in the data center. The other is a trend to move the compute closer to the source of the data, which is kind of using collectors and the intermediary computing blocks, right, like baseband units. Uh, Now moving on, I'm taking you on this journey, taking you inside the data center, and I think this is a good slide to get an appreciation for how the compute and what's driving the compute inside the data center. Yeah. So when we look at the connectivity inside the data center, you have the high performance switches that connect between data centers. So that's where data comes into the data center. Then you have the data center racks, which basically contain the CPUs, the graphics processing units, which are now doing a lot of the compute also for AI. And then you have FPGAs, which are programmable, and then the ASICs, which are purpose-built silicon. So from an application perspective, the compute pretty much happens in the CPU, GPU, FPGAs, and AI rack AI purpose-built processors, and these take place in the servers and racks. The networking obviously takes place on the switch side, and also in the optical modules, and then on the storage side, with the emergence of flash memory and cold storage for hard drives. There are racks of storage that are being deployed inside the data centers. So when you look at this, the key trends is that the move towards disaggregation is another key trend in the data center, because typically what you would have is an integrated server which would have the CPU, storage, and the memory all in one. Now, with the disaggregation, you have dedicated compute blocks, you have storage farms, and then you have memory. And all of these can then be used for specific applications and shared within the data center. What that does is it creates a tremendous amount of traffic inside the data center to share the data, and that drives more need for connectivity. So with this context, I wanted to give you a context of why purpose-built custom SoCs are rising inside the data center and in these applications. And let me take you through a tour of that. So the interesting thing, if you look at almost every data center SoC, they all have these common building blocks, right? And when you look at them, each data center SoC has some form of a compute, which is a processor. It has a host interface, which is a PCIe or CXL that connects to the host processor like a CPU. And then you have an Ethernet or a network interface which connects to the switches and moves data around or connects to other chips that also have network interfaces on them. And then you have the memory subsystem, which is DRAM. And all of these are increasing in importance because there's more compute, there is more communication with the host, and there's a lot more traffic in the data center. And memory is very important, especially when you do things like AI training and so on. Right? So it seems very simple, uh, but when you actually look at the reality, there's a lot of complexity behind this. And the reason for the complexity is when we look at the different applications, right? Each application has different trade-offs when it comes to bandwidth, when it comes to power consumption, when it comes to density and cost. And then if you look at the bottom, things like latency, how robust the link needs to be, and the reach. So for example, if you're driving chip-to-chip connectivity, you need very small reach between the chips. But if you're driving from a chip to a backplane or driving across data centers, then you need a lot more longer links. So, when we design these silicon, when we design chips, we cannot. It's very difficult to design one class of chips that meets the performance requirements of everyone, and and that drives the need for optimization, which has become very important because power is important, bandwidth is important. You increase the bandwidth, but then you cannot increase the power exponentially. So a lot of these techniques need optimization. So from that point of view, since they all have different trade-offs, many of these trade-offs are conflicting, and it's very, again, as I mentioned, it's very difficult to have one solution that can meet all. So the answer to that, and that's one of the reasons why, if you look at a lot of the hyperscalers or if you look at a lot of the industry, there's a lot more configurable and customizable chips that are coming out, right? Configurable IP, configurable SoCs that have been introduced into the market. And this is a trend where Alphawave is very focused on in delivering solutions that enable our customers to optimize for all the parameters that I talked earlier. And if you look at the simple block diagram that we had talked about in the previous slide, this maps us. We have mapped our solutions to this. So when we look at it from on the left side, we have the optimized subsystem, which has very low latency, and those are typically PCIe, and the state of the art for PCIe today is PCIe Gen 6. With the emergence of CXL, we have CXL-based solutions uh, that enable you to do very low latency connections with and coherent access other chips coherently. On the right side is the Ethernet subsystem, where this is another very strong area for Alphawave. We have uh, configurable IP, DSP-based IP that we can do. And today, these transceivers are running at 112 gigs. Now they're running the next generation of these will be at 224 gigabit per second. Last but not the least is also memory. One of the key things when we do AI algorithms is these things require a lot of memory and sometimes they require a very high bandwidth. So that is another key area where that has led to the emergence of things like high bandwidth memory, HBM, where we offer HBM3 application optimized controllers. These come with 2.5D packaging, so it requires a combination of packaging, memory technology, and custom silicon. And then, of course, there is other technologies like DDR that are also coming up. So what is the key to enable all this? You know, the things that enable these are custom silicon and the IP. And one of the other key things that also enables this is the transition towards smaller process geometries. The state of the art today is 3 nanometer integration, more of things. So many of the chips that are coming now, the chip sizes have increased to more than the reticle size. So these are like very high uh, size chips. And then also the need for advanced packaging. And things like CoWAS from TSMC or InfoOS are new types of packages, which we will have separate webinars to talk more about in terms of packaging technologies. So Alphawave offers a complete custom silicon solution, which integrates all of these together with our accelerated connected IP. Uh, so when we had shown you the block diagram of what's in there, the key IP are the PCIe Gen 6 for the servers and the storage connectivity. On the networking side, we have 400, 800, 1.6 terabit per second Ethernet IP, which includes the PHYs and the controllers. And on the memory side, we offer subsystems, which include the HBM and the DRAM PHYs. And the same thing on the chip. I'll talk about chiplets, which is another huge trend, which is driving more custom silicon and IP designs. So we'll switch gears a little bit and talk about chiplets. I think many of you have already heard of this. I'll give you a quick overview of this and then talk about what we're doing in that space. When we look at the single chip solutions, chiplet solutions, uh, because of the drive towards more and more integration, we're seeing that the increasing amount of compute is causing chip die sizes to be very large. And the problem with that is they become larger than reticle size. And also they have the large dices cause low yield. And then the other thing is because if you need to get a lot of data in and out, you need to add more SerDes channels, but then you become bandwidth limited because you cannot put so much I/O on these chips. And then also what happens is your time to market is constrained because these chips are becoming so complex. Some of the IP may not be available in the latest node. The cost of these things increases. So all of these cause certain limitations, and we are starting to hit a wall, right, for which that. And that's where the rise of chiplets come up, where we take these big die and break them into smaller die, and then we have these scalable architectures that uh, add the dies to increase the performance. So this is a much more cost-effective solution, and it reduces time to market by combining the existing SoCs with some other available die. Um, and there are different types of chiplets. In this case, in the left side, we basically break this die and then we combine them into smaller ones, right? On the right side, which is another trend, which is more, I think, more prevalent trend right now, is you increase the bandwidth by creating higher chiplets. So you, instead of putting all your transceivers on the main die, you take it and put it onto the uh, smaller chiplet die. And this enables us to reduce development costs by sharing these IO chiplets across multiple nodes. And this is an example of what I was talking about earlier. The left side here contains a full monolithic SoC, and the right side here shows a view of the chiplets, right, along with the IO chiplets and the accelerator chiplets and the memory chiplets, along with the main AI compute die. So in this example, in this case, for example, we would have a main AI compute chiplet that is developed by by one of our customers. Alphawave delivers the IO chiplets and the accelerator chiplets and the memory chiplets, right? Which which then enables a complete system to be delivered to the customers. So what we're seeing in terms of trends here is a more of a plug and play approach, which leads to more wider adoption because now rather than by having access to these chiplets, you can do more in terms of plug and play. You can take your main die and combine them with some chiplets, which can then be shared either across your company or with other customers. So you get cost savings, faster time to market. And then it also allows you to differentiate because now you can put multiple SKUs on this. You can improve your performance based on what you need. And of course, your ROI goes up because now you don't have to invest in all of your designs 3 nanometer mask set, for example. So from Alphawave side, in order to enable this, we are developing we are making investments in pre-built chiplets. Some of these we're collaborating with customers, some of them we're doing ourselves. So these are very targeted to focus market segments. So one example of this would be the IO chiplet, where we disaggregate the logic and the IO. And in that case, we integrate the PCIe and the Ethernet, and then we connect them over die to die. So these chiplets are now connected to the main die through a die to die interface. The key advantage of this is that we can stay with the IO chiplets in an N-1 node, which is, for example, the main processor can be a 3 nanometer SoC, but the IO chiplet can be in a 5 nanometer or even a 7 nanometer SoC. And the similar concept applied to memory. One of the key trends now is using memory expansion with CXL. And by doing a memory IO chiplet, for example, you enable you to expand your memory bandwidth by using these chiplets, and you can make them scaling it. It also, with the emergence of CXL, you can also have coherency with your CPU, which means that the CPU can access the memory on your chiplets in a coherent manner. Finally, on the right side is an accelerator chiplet. What this computes is in many AI applications, you need a co-processor or an accelerator that does certain functions. And that accelerator, the processing of that accelerator can be put onto an accelerator chiplet. And then that connects with the main processor using PCIe and DDR interfaces. So I think I gave you a good overview of why custom silicon, the memory trends, and then how chiplets can be combined with customer designs to realize functionality of a large homogeneous chip. Having said that, I want to do a wrap up of what we learned today. We talked about data center connectivity, the trends, how semiconductors are key enablers for that. You understood also why it is difficult to have a one-sized approach, even though all data center SoCs look alike. The difference is in the performance, the power, and the latency and some of those other trade-offs. By using custom silicon with our differentiated IP, high performance IP, we can achieve those customizations. Talked about the role of rising role of custom silicon and IP, and the emergence of chiplets in the ecosystem. So to learn more about it, you can visit our website at awavesemi.com. And also you can contact us at the email address we have shown below. So I appreciate you taking the time, and we look forward to the next part, which is the Q&A section. Thank you.